Hi, everybody. I wanted to give you a little bit of insight into your kinetics worksheet that you're going to do. The intent of this worksheet and the purpose of this worksheet is to give you the opportunity to look at some data and plot it and generate a pair of graphs. Um, those graphs are graphs that you've seen before in your first semester biochemistry course, Michaelis-Menten and a Lineweaver-Burk plot. But I wanted to just kind of give you a sense of what those graphs are ultimately going to look like. So you're going to get an Excel spreadsheet that has a couple of things. One thing that it's going to have is a column that shows V sub 0. V sub 0 and numbers underneath that. X, 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 X. So your V sub 0 is your initial velocity. Now that's your enzyme's initial velocity, and that is a tangent to your average velocity, but at your zero time point. What you're going to be doing is you're going to be plotting that versus your substrate concentration, which I'm just going to denote as S. And there will be data there indicating, well, what happened or what was the initial velocity of our enzyme when our substrate concentration was this. Then what was our initial enzyme velocity when our substrate was this, and so forth. And with those two things, what you're going to easily be able to produce is what's known as a Michaelis-Menten plot. The Michaelis-Menten plot is going to be on your y-axis, V sub 0, and on your x-axis, your substrate concentration. This is a plot that you'll be able to generate this, and it will look a little bit like this, roughly. Now, what you should immediately notice about this is that your data is not linear. Sure, there might be a linear range to it, but the overall display of your data is not linear. Instead, it's going to have a hyperbolic curve. So it goes up and it basically plateaus. Now, with that in mind, this is valuable information because what you can do with this is you can look at your y-axis and you can see roughly where your velocity kind of hits its peak, where the velocity, no matter, relating it to your substrate concentration, where the velocity is. As long as the substrate concentration keeps increasing, your velocity never increases. It reaches a V max. Now, V max is an important kinetic parameter for any enzyme that you study. You want to know basically how fast can this enzyme possibly go whenever we give it an infinite amount of this substrate. That substrate is going to be like no matter how much extra substrate we add, the velocity simply is not going to increase. Now, as soon as you have your Vmax with a Michaelis-Menten plot, what you'll also be able to do is you'll be able to look at on the y-axis, where's half of Vmax? Well, it's about right there. Halfway up the Vmax is where, I don't really know how to define it any further than that. Halfway up the Vmax, halfway up the y-axis is your Vmax. What you'll be able to do with that is come up with a coordinate, come up with a point that relates to that, and relate what is the substrate concentration at Vmax. When you know your substrate concentration at your Vmax, effectively what you get is something known as your Km. Now, Km, in addition to providing you the substrate concentration at half of Vmax, it also gives you a little bit of a measure of affinity that your enzyme has for that substrate. So the lower the Km is, the higher the affinity that your substrate or your enzyme has for that substrate. The higher that your Km is, well, then the lower the affinity it has. So these are two data points, or these are two kinetic parameters that are very important for studying enzymes, Km and Vmax. How fast can your enzyme go, and how much substrate does your enzyme need to get there is another way of looking at that. So you'll be given this data and you'll be able to come up with that plot. Now, the other plot that you'll come up with is what's known as a Lineweaver-Burk, which I'm just going to, Lineweaver-Burk plot, which is also known as a double reciprocal plot. I'm just going to label it as an LB plot. In your Lineweaver-Burk double reciprocal plot will look a little bit like this. 1 over velocity, initial velocity versus 1 over substrate concentration. And so this data set that you have right here, all that you're going to do is take your initial velocity data points, and you're going to take the reciprocal of them. So 1 over, 1 over, 1 over. Now the other part of this is you're going to take your substrate concentration and take the reciprocal of that, 1 over substrate concentration. So 1 over this, 1 over this, 1 over this. And ultimately, you're going to come up with a plot of data that looks a little bit like this. Effectively, what you're doing is you're taking this data that is not linear, as displayed by our Michaelis-Menten plot, and you're going to make it linear. And you're going to get something that looks like that. Now, again, this is a valuable representation of your data because what it enables you to do is it gives you a little bit more of a concrete way to calculate your Km and your Vmax. Whenever you plot a graph and come up with a line of best fit, you'll come up with a y equals mx plus b. Now, in order to solve for, or in order to use that, it's important to also know that your x-intercept is equal to negative 1 over km. And if you look at this, my number here is in the it's in the second quadrant, and it's actually a negative x value, which is just fine. That right there, let's say hypothetically that your x-intercept is negative 2. Set that equal to negative 1 over km. Do the algebra, and you find out that negative 2 equals negative 1 over km leads you to, well, km equals 1 over 2. Now, our other kinetic parameter, our Vmax, our other important kinetic parameter right here, or sorry, is displayed right here. And that's 1, that is your y-intercept, 1 over Vmax equals your y-intercept. So what that brings us to is, let's say hypothetically your y-intercept is 3. 3 equals 1 over Vmax. Well, then your Vmax is equal to 1 over 3. Now, add to that, if you have your y equals mx plus b, this equation right here. If you've plotted your data, what you can do is you can figure out, well, what is my x-intercept and what is my y-intercept? Your x-intercept is going to be whenever y equals 0. So what you would do is if you're trying to solve for your x-intercept, you would plug y in for 0. If you're trying to solve for your y-intercept, what you would do is you would take x equals 0 and plug that in here and solve for y. And as soon as you've solved for y, then what you have is equals 1 over v max. So when you have that y equals mx plus b, that's powerful for determining your x-intercept and your y-intercept, but it's important to think about that graph and say, okay, when my y is equal to 0, that means that I am effectively right here. Therefore, x is this. Okay, so I'd solve for that. When y equals 0, I solve for x. X then is equal to my x value is equal to negative 1 over km. Chances are your x value there is going to be a negative value. All right, well, I hope this is helpful, and I hope that this is a solid direction on how to manipulate and work with the data that you're going to be provided with. If you have any questions, though, please don't hesitate to ask, and I'd be glad to help you out. All right, well, have a good one.